carbon around the 300 part per million level, then we will know for sure that the planet's temperature, as we know today, will still be the same. So that kind of is tying in global warming and the issue related to carbon emissions and CO2. All right, let's go to the next slide. So we talked about inorganic carbon being converted to organic matter, and over geological time frames, this organic matter has been converted to fossil resources, petroleum, natural gas, coal, and we use it and we put it back into the atmosphere as CO2. So fossil resources, petroleum, natural gas, and coal, is also natural. It's part of the same biological carbon cycle. So we cannot say that biomass is natural, so it is good, somehow making fossil resources artificial or something bad. The issue really is very simple. The rate at which I fix inorganic carbon is in a 1-year time frame, then converting that organic carbon to fossil resources is in millions of years. We use it and we put it back in a 1 to 10 year time frame. So you can see the math is very simple. The rate at which I fix inorganic carbon to fossil resources is in millions of years. The rate at which I fix carbon to this is in 1 to 2 year time frame. We use it, we put it back is in decades, 1 to 10 year time frame. So what we are talking about is that by using a renewable feedstock, which is biomass agricultural feedstock, we can fix carbon within 1 year time frame, use it, put it back, and plant another crop in the next season to fix that CO2. In other words, we can be carbon neutral. When you use a fossil resources feedstock, as we are seeing on your slide, then the rate at which I fix is in millions of years, and the rate which I use it and put it back is in 1 to 10 year time frame. So the rationale is that by using a renewable feedstock, renewable carbon feedstock, the rate at which I fix inorganic carbon equals the rate at which I use it and put it back. That, ladies and gentlemen, is a fundamental intrinsic value proposition for using a renewable bio-based feedstock as opposed to a fossil resources feedstock. All right? So think for a minute. You are making, or you're a manufacturer of products, or you're a user of products, and what I am submitting to you is that if I can make that product using a biorenewable feedstock, then anything which the rate at which I fix that carbon will equal the rate at which I use it and put it back. So I make a product out of a renewable feedstock, I simply burn it and put the carbon back into the atmosphere as CO2. I plant another crop to fix it, I am carbon neutral. So that is a fundamental proposition in switching from a fossil feedstock to a bio feedstock. Let me explain that in a different way as we go along. So in this slide, what I'm showing you is the carbon footprint, kilograms of CO2 per 100 kilograms of plastic released, okay? If you use a petroleum-based plastic, polypropylene, which has got a carbon content of 85.7, the amount of CO2 released per 100 kilograms of plastic is around 320. You can see that. For PET, it is 240 kilograms of CO2 per 100 kilograms of plastic. In the case of starch PLA, it is 0. You can see that. Why is it 0? Because we just said if you plant another crop, as soon as I use it to make my product in the next season, I'm going to fix it. So the time scale is within 1 to 10 years, I am carbon neutral. If I took a fossil resource feedstock, and eventually I'm going to have to put that carbon back into the atmosphere as CO2, then I do not fix it back to coal or oil or any of the other fossil feedstock in the time scales we are talking about. So you will always be putting out 320 kilograms of CO2 per 100 kilograms of plastic as opposed to a bio feedstock. The take-home message is very simple. If we use a bio feedstock, you have the potential, and the key phrase is potential, to go to a zero carbon footprint at the beginning of your process. If you use a petroleum feedstock, no matter what you do, you will be at a 320 kilograms of CO2 per 100 kilograms of plastic released to the environment by using a petrol feedstock. All right? That's the fundamental lesson on this slide. Now, if that is so simple, why are we having a problem willing to switch to it? The issue comes as follows. So, we just talked about the intrinsic value proposition for using a bio feedstock. However, we don't use feedstock. We have to make product. So, the feedstock has to be converted to a product. The product has to be transported to the consumer, and then it ends into an end of life, right? Transforming it into useful product. So, in order to convert the feedstock to product and to end of life, we are going to need energy, and we are going to put out emissions. And that is the issue. So, while you may have a zero carbon footprint, as you are seeing there, the conversion of the feedstock to product and transforming it in the end of life into a useful product or something, we are going to consume carbon energy and we're going to put out carbon emissions. So, the conversion cost has to be such that the amount of CO2 released per kilogram of plastic must be equal to or less than what you're trying to displace. So you may start with zero, but if in the process of converting the feedstock to your product and its ultimate end of life, you put out more carbon emissions, you use more carbon energy, then you're defeating the very purpose of why you're using this. All right? Now translate this into a different way. So we talk about reporting carbon footprint, reporting total environmental footprint. These are ASTM standards. We'll talk about that in a minute. So in the slide is in front of you, you're seeing the same three products: starch or a PLA-based product, a PET-based product, and a polypropylene-based product. The light white or light area shaded is the CO2 released per 100 kilograms of plastic. So you can see that that's the light shaded areas. Now here's the interesting thing. In converting the feedstock to product, which I call as feedstock CO2 release, for polypropylene is around 150 or 200 kilograms of CO2 per 100 kilograms of plastic. In the case of starch PLA, you can see that the CO2 released per 100 kilograms of plastic is about 400 kilograms of CO2 per 100 kilograms of plastic. If you are a polyolefin producer, you say, look, I use only about 150 kilograms of CO2 per 100 kilograms of plastic, whereas yours in the bio-based, you're using 360 kilograms of CO2 per 100 kilograms of plastic, so you are nowhere any good. But look at the blue part in front of the polypropylene. This is the intrinsic feedstock CO2 released to the environment, because the rate at which CO2 is fixed is in millions of years. The rate at which it is used and put back is in 1 to 10 years. So the total, the blue and the white area, translates to about 520 kilograms of CO2 released per 100 kilograms of plastic for polypropylene, whereas for the starch PLA it is around 320. So you get the point that the feedstock releases a lot of CO2, which when combined with the conversion is much higher than if you use the starch PLA-based product. Now take the converse of it. If the starch PLA product manufacturing is more than 520, then you have defeated the very purpose of switching from a petrol feedstock to a bio feedstock. That is where the message is. So fundamentally, what I'm saying is the following, and I hope the message is coming clear to you all, that the combined feedstock CO2 released with the conversion CO2 released is the total carbon footprint, and combining that with the bio feedstock will give you a better value proposition, provided you make sure that in the conversion of the bio feedstock to your product, you're not using up more carbon energy and you're not spewing out more carbon emissions than what today's products' carbon energy consumption and carbon emissions are. That's the value proposition. All right? Let's go to the next slide. This is an example from the NatureWorks data on the life cycle of polylactic acid, and I want to present it to you in a different way. The first part there, which says PLA5, that relates to the PLA5 is right here, and the amount of CO2 released per kilogram of plastic is 2.02. So the units have changed a little bit here. It is per kilogram, not per 100 kilograms. So PLA5 puts out 2.02 kilograms of CO2 per kilogram of plastic. All right. Now, remember, if you now improve technology, they are projecting that the 2.02 will go to 0.75, will go to 0.27 when I switch to a renewable energy in place of a fossil energy, and finally you see that you can combine the two and you can even go to a negative CO2 release. The point here is as follows. Your process today to convert bio feedstock to product may be high, like 2.02 kilograms of CO2 per kilogram of plastic. However, if you can continue improvements, switch energy, and you can go to a zero carbon footprint, your best choice would be a bio feedstock. If you use a petroleum feedstock, then you will always have, and you can see that blue in this slide over here, for polypropylene, for example, you can never go below 320 kilograms of CO2 per 100 kilograms of plastic. That will always be a negative to use of polypropylene in terms of carbon emissions to the atmosphere. So your carbon footprint will always be higher than 320 kilograms of CO2 released per 100 kilograms of plastic. All right. I will illustrate this in the slide which comes up. For example, let's say you make a pen. One pen puts out 15.7 grams of CO2. If you say, I make enough pens, this is for a company we did, then you put out 5,735 tons of CO2. If you switch to a biocarbon product, then you can reduce